Hi students. Wrapping up lesson 5, this is video F. A couple of examples. We've learned the definitions. Let's go to the sideboard in just a minute. Let's do a couple of examples and call this lesson over. All right, example. Cecil County has 10 zip codes. 3 were selected by the postmaster. Inside each zip code, 5 neighborhoods were picked randomly by a computer. And in those neighborhoods, the Saturday mail was postponed until Monday. So there's been some talk of Saturday mail just getting canceled. And so they're running a little trial here. And they did it for the month of June. Post office officials tallied up the number of complaints by residents to determine if Saturday delivery is still a necessity. Okay. So let me read the 3 and then we're going to go over to the sideboard. In part A, we're going to draw a diagram, big circle for the population, little circle for the sample. And then part B, identify all methods of sampling used in the problem. So previous video we learned about simple, random, cluster, etc. And finally part C, can we think of any problems, any potential sources of bias? All right, so we'll go sideboard here. All right, so put the population here. Right, this is the big group. Make the circle as big as possible. And I suppose we could easily cancel the Saturday mail for everybody in Cecil County, but we're not going to do that. We're just going to take a sample. So here's the smaller circle for sample. I have to make it big enough so I can write what I need to write in there. But big group, population, small group, sample. Remember the letters we've got to get the symbols right. Capital N is population size. I don't know how many postal customers there are in Cecil County, but this would be all of them. Right? All the postal customers in the county. Thousands for sure. When we take a sample, the sample size will denote with small, lowercase n. Okay, so make sure we get that right. This is the smaller group. And from the description in the problem here, I don't know the number of people that were sampled, but I'll try to write it out in words. Right? This is those customers actually selected. Okay, now what did we do? We took 3 out of the 10 zip codes, we took 3 of them, and for each of the 3 zip codes, we took 5 neighborhoods. So this is probably a couple hundred businesses and houses if I had to guess. All right. Numbers that describe the population are called parameters. Think about the variable. The post office is sort of waiting by the phone. I'm not sure if this is the best way to collect data, but they're counting up the complaints, right? Every house either complains or they don't complain. So whenever we're dealing with percentages, like percentage of people who complained, we can call that P, lowercase p. And this is a number that describes the whole population, all of Cecil County. P would be the percentage or proportion of all residents who would complain, or more generally, I don't know if you need to actually complain or not to feel that Saturday mail is important. So possibly in parentheses, percentage who want that Saturday mail. Could look at a couple of different things. This is probably the true number that we'd want to understand, right? The percentage who want Saturday mail. But in this problem, we're told that they're going to wait by the phone and see who calls up to complain, where's my Saturday mail? Now, over to the sample. These are the folks that were picked from the neighborhoods that were picked. And I will be able to count up the number of complaints from the neighborhoods, right? We'll call that P with the hat on top. That's the percentage from the sample. P all by itself would be the percentage in the population. Remember, typically these numbers are unknown. Once we collect our sample, the value of P hat from the sample, we will know that one. And so this is the percent who complained in the 5 neighborhoods. Or more generally speaking, like I had the in parentheses here, it'd be the percentage, I guess, who would want their Saturday mail in the 5 neighborhoods. Okay? So here's a picture. Remember, population, big group, with parameters. Both start with P. Samples, the small group, lowercase letters, and these are called statistics, right? Parameters, population. Statistics go with the sample. Okay. Part B then, identify all methods of the sample used in the problem. Let's think about this. Cecil County has 10 zip codes. 3 were selected by the postmaster. So if I break Cecil County into the 10 zip codes, for part B here, selecting those 3 zip codes is a cluster sample. So we broke the county down into groups, and those groups were zip codes. And now we're picking 3 of those. And we can call this a cluster because the first stage of this sampling process, we're basically taking the whole zip code as it is. Okay. Once we picked the 3 zip codes, what happened secondly was that we picked what? We picked 5 neighborhoods. And once the 5 neighborhoods were picked, every house in that neighborhood was, well, the Saturday mail was stopped, right? So picking the 5 neighborhoods is also a cluster. Since I'm doing 2 things sort of in sequence, technically this is multi-stage. Students, I'll give you a hint. If you give the one-word answer for part B and you just say multi-stage, we don't typically offer much credit for that. We'd like the details. Okay? Now, I could see an alternative answer for this top part as I'm thinking and writing here. Though it doesn't really say it in the problem description, you could almost view this, if we knew the details of how the 3 were selected. Let's say they put the 10 zip codes in a hat and just picked out 3 of them. You could call this simple random to start, just picking those 3. We don't have enough details to really understand this fully. I would probably accept either one of these answers for part B. The second part of this clearly is a cluster by neighborhood. All right, so that was part B, identify all methods of sampling. Finally, part C says to list any potential sources of bias. In other words, what could go wrong? Would the way that we selected our data make this sample not representative of the population? And I don't know. A lot of this is subjective. We don't know how the 3 zip codes were selected. So if for some reason these zip codes don't really represent all of Cecil County, then the sample will certainly be biased towards these zip codes, right? So there could be some zip code biased. I've never been to Prince George's County, but I'm guessing Cecil County is much different than Prince George's County. So if the 3 zip codes were all like Prince George's County or Frederick, might be very different than say, Cecil County and some of the more rural zip codes. Another thing I thought of here, it's got to be some voluntary response bias. Think about who's really going to call up the post office to complain about the mail didn't come on Saturday. It's going to be those residents that really want the mail on Saturday. I'm thinking of myself, in fact, if I didn't get my mail on Saturday, I probably wouldn't even know it. I would just think I didn't get mail that day. So think of all the residents in the neighborhoods. Those that are willing to call up the post office and complain might feel very differently than the general population of most of the people living in the neighborhoods. Okay, so I think the way that the post office decided to collect this data, they might not get to the heart of the matter, right? If they really want to know what percentage of the population wants Saturday mail, I'm not sure if stopping Saturday mail for a select number of neighborhoods is the way to investigate that problem. All right. That's the first one. There is one more. We'll go back to the center slide here just to get that problem description. And all right, so example 2 to wrap up this lesson, ways to sample data. In a warehouse, quality control managers randomly select 8 cases of Cool Ranch Doritos from the pool of all the day's manufacturing. Every bag in the 8 cases is weighed to ensure that the bag filling machinery is working properly. As you know, every time you buy a bag of chips, sometimes it seems like the bag is stuffed, and sometimes they're all half empty when you open it up. Once the bags are weighed, the manager grabs one from each case, opens it up, and inspects it for broken chips. Okay. It's the same 3 tasks, I do believe. Let me double check that here just to make sure. Draw a diagram of population and sample. Part B, identify all the methods of sampling used in the problem. And finally, part C, list any potential sources of bias. Okay, so we'll do it one more time. Solidify our understanding of these definitions, and this should free up some time in class to do some interesting activities. All right, so here we go. Population, the big group. We'll make the circle bigger. Here's the population. Again, I don't know how many bags of Doritos that this plant makes on a daily basis, so I can't put a number to this, but capital N would be all bags produced. If you're in the Dorito manufacturing business, you're making Doritos every day, right? So all bags produced, you're doing quality control every day. I'll just put that day. When the day's over, we come back tomorrow, we're going to make new Doritos. We sort of have a new population, right? From this population, we're going to do quality control. So here's the sample. Sort of looks like that time. Lowercase n, this is a symbol for sample size. Again, depending on how many bags of chips are in a case, I don't know, so I can't really put a number to this, but I do have 8 cases, right? Little n is those bags picked that day. If there's 24 bags, I guess 8 cases times 24 bags in a case, possibly, I don't know, but right, that's the sample size. We're doing 2 things here. Number 1, we're making sure that the bags are weighing approximately what they're supposed to weigh. Right on the bag is printed how many ounces of Doritos you're getting in the bag. So there's some parameters here that we would be interested in. One would be bag weight. We certainly want to make sure our machinery is filling the bags properly. We can't weigh every bag, so we take a sample just to double check and make sure that the sample is in line with what the population should look like. Bag weight is quantitative. The best way to summarize a quantitative variable typically in this instance is to look at the mean. Okay, so I will use the symbol for population mean. That symbol is mu. In case we haven't covered this yet, I will just say that this is, if you were to spell this out, it's mu. It's the Greek letter for M. And for populations, typically we use the Greek letters, and so this is the Greek letter M for mean. Okay? Probably we've seen this at this point, but just in case, get that in there. The mean would be, right, mu would be the mean weight of all bags made that day. If I'm running quality control, this is a very important number to me, right? On the bag, maybe it's printed 28 ounces of Doritos, and so from everything we made that day, I want to make sure that my mean weight's pretty darn close to 28 ounces before we're shipping these bags off to the store. We won't weigh all the bags. What we'll do is we'll take from our sample, those bags will get weighed, and be careful here, the symbol is Y bar. When we're talking about a sample, the symbol is Y bar. When we're talking about a population, the symbol is mu. And you've got to get the symbols right. They are important. This would be the mean weight from that day. The idea goes like this. As long as I take a good random sample of bags and weigh them properly, this number should be a very accurate descriptor of what's happening in the population. Clearly, the value of Y bar is not going to be precisely the population mean, but as long as this isn't too far off what it should be, then we'll probably feel good about the day's production and we'll go home. If the numerical value of Y bar is way high or way low, then that's going to be a clue that this sample is telling us that something's wrong with our production, right? So as we develop these ideas in this course, you could sort of, it's a foreshadowing of where we're going with the material. There's one other thing, there's a second parameter here that we're looking at, and remember part 2 of this process was once the bags are weighed, a manager grabs one bag and opens it up and sort of looks, sees if there's a lot of broken chips or not. I guess that's a thumbs up or thumbs down, like either the bag looks fine or something's off, all the chips are broken. Because that's not a quantitative variable, it's sort of a yes or no, it's categorical, then we would summarize that again with a percentage or a proportion. So that number, the parameter would be P. This would be the percentage of bags that are, quote, okay for all of the bags. And hopefully that percentage is a very high percentage, very close to 100. Once I collect my data, I could summarize that. I'll call it P hat over there in the sample. Again, there's a difference, and it's important. And this would be the percentage of those bags that are okay. Percentage of the bags in the sample that are okay. If this is 100% or high 90%, then we'd probably feel fine that in the whole population things are working smoothly at the plant. You know, if this is, say, 3 out of the 8 bags that were selected, there's a ton of broken chips, then they're probably going to look for problems in the population, right? We're gaining clues about the nature of the whole population from the sample. All right, B and C, and we'll call it a day. Part B says identify all methods of sampling used in this problem. What did we do here? I take all of my production and I'm selecting 8 cases. Once those 8 cases are selected, every bag in the case is weighed. I must have had cluster on the mind when I wrote this example because we're cluster again here. This is cluster by case. We're presuming every case of Doritos mimics the population. So what I'll do is I'll randomly pick 8 cases and I'll weigh every bag in those cases. It's clearly a cluster. The next step, once the bags are weighed, the manager grabs one and opens it. I would say the best answer is this. I cannot imagine in my wildest dreams that the quality control manager is numbering the bags 1, 2, 3, 4 up to 12 and getting his or her calculator out and randomly selecting bag number 18 and picking that bag, checking it for broken chips. My guess is the person just grabs a bag and pops it open. Officially, it's convenience. I don't think there's anything wrong with the way that this is being selected, but we've got to make sure that we don't call it something that it's not. Remember, simple random sample has that really precise definition, and I don't know that we've met all the requirements the way that this problem is described. Again, I'm doing one thing and followed by a second. This is multi-stage. But please, students, if you give the one-word answer, we're looking for details. You might get 1 point out of 5 or something for just the one-word answer. I need to know each piece and what the method was. All right, to wrap up, sources of bias. When we cluster by case, I can't really imagine too many things that would go wrong. It's a great way to sample here. We're presuming all the cases are mimicking the population. When we're randomly picking or convenience sampling one bag out of each case, I don't really see much issue with that. A few things I can think of, we always have to be thinking how we're collecting our data, but is your scale calibrated? I'll say working properly because I can spell those words. You know, there could be scale bias. You have to check your equipment to make sure you're not getting measurement errors. What else could go wrong in this situation? Maybe the person that inspects the bags is just lazy and has never given a bag a thumbs down, right? So there could be some inspector bias. I don't know. Perhaps this is an exemplary employee and does the right thing every time. Or perhaps just pops the bag open and always gives it thumbs up for broken chips. Okay? When you're asked to list sources of bias on take-home quizzes, just the bad answer is there's nothing I can think of, or none. There's always things that can go wrong. So we'll just encourage you to put a little thought in if we ask you for some potential sources of bias. Think it through. Try to think of some things that might go wrong. Okay, so I do believe that finishes up lesson 5. Thanks for watching and hang in there.